So what is linear programming problem? A linear programming problem in math is a system process of finding a maximum or minimum value of any variable in a function. It's also known by the name of optimization problem. This definition is given by Mr. Ravina Pans, an assistant professor at the ARSD College, and the problem is generally given in a linear function which needs to be optimized subject to a set of different constraints. So linear programming is a problem-solving approach, and that's used by managers to make the decisions using the scarce resources. And here is a small model to it's about a linear programming problem. It includes the three main parts. So now we will discuss about three main parts of linear programming problem. It includes decision variables, objective function, and constraints. Decision variables are the variables which are changeable and going to impact the decision function. And for example, the profit function is affected by both sale and price, and sale and price are changeable and they impact the profit. So sale and price are decision variables, and the objective functions they are related to either to maximize or minimize. Maximize, for example, like profit, sales, production, or etc. Minimize like cost, loss, energies, consumption, and wastage, etc. And for the constraints, there are any kind of limitation or scarcity explained through a function, like limitation of raw materials, time, and funds, equipment, etc. So I will give you more details about the objective function. The objective function actually is a mathematical equation that describes the production output target that correspond the maximization of profits with respect to the production. Then use the correlation of variables to determine the value of final outcome, or simply the objective function as a numerical mathematical expression for the objective that was to be achieved by the program. And of course, the objective function of a linear programming problem is a linear function of the form like z equal ax plus by plus bi. And as we mentioned, maximization like profit, rate of return, effectiveness, and minimization is related to cost like time. And for the constraints, we have two types of constraints. They are availabilities and requirements. The firstly, availability constraints. They are the restrictions on the variability, like the constraints are on the machine capacity, on the machine hours, or maximum raw material availabilities. And requirements, they are the restriction, like requirements from the company, from the contracts, like the number of packages of meat produced each month cannot exceed 90,000. Or they can divide it into three main categories. They are natural constraints like capital limitation, dividend disbursement, etc. And for the economic constraints, they are types of external constraints, and they involve external economic factors that affect a company, and they are usually outside of its control. And actually, a company influenced by both microeconomic and macroeconomic factors in its external environment. And it's, for example, like tax rate, inflation rates, unemployment rates. And if unemployment are too high, so our sales may suffer. And so because people can't afford your products, so you need to adjust it. And for the policy constraints, the policy constraints is an internal rule that keeps a business from maximizing the amount of throughput, the amount of material that is generated. The policy constraints come from the requirements from contracts or state security commission. For example, the policy constraint is like minimum production run. As we know, all the production run must generate a certain minimum number of units. So the policy constraints set a certain minimum number of units, which is supposed to appropriate with the equipment setup cost. Because in reality, a larger production run just drops or just take the next drops in light of valuable machine time and may also create assets inventory. So the next part is formulation of a linear programming problem. They include three steps. Step 1 is identify and define the decision variable for a problem. In this part, we will define the variable completely and precisely. This is very important, and all the units of measure need to be stated explicitly, include times units if appropriate. And for example, if the variable present quantities of product produced, so these should be defined in terms of tons per hour, unit per day, barriers per month, or some other appropriate units. Step 2 is to define the objective function. In this step, we determine the criterion for evaluating alternative solution. This means we determine that what goals, what is your goal and what is your purpose, like maximum or minimum, and the objective function will normally be the sum of terms made of a variable multiplied by some appropriate coefficients. And the coefficient might be the profit per unit of production, distance traveled per unit transported, or cost per person hired. And the final step is identify and express mathematically all the relevant constraints. We will express each constraint in words and substitute the appropriate numerical coefficient, like greater, smaller, or equal, and variable names for written terms. For example, the constraints are minimum requirement of the vitamins. The minimum requirement of vitamin A is 8 units, for example. So therefore, is 3x plus 4y is equal or greater than 8, where x is kilogram of food 1 and y is kilogram of food 2. So now to understand clearly, we will illustrate an example. The example about the furniture company C. This company produces only 2 products, product 1 and product 2. It is assumed that all amount produced are consumed in the market. So how much product 1 and product 2 should the company produce if they want to reach the maximum profits? And for example, the profit per unit for product 1 and product 2 is $56 and $40 respectively. Each share requires G1, G2, G3, G4 spare parts, and chair legs. And according to the contracts, total amount produced are not lower than 100 products. And here we have a table about chair parts, the requirement of chair spare parts of the product 1 and product 2, and total use. So the formulation of linear programming model. Step 1, identify and define the decision variable for a problem. The number of units of product 1 and product 2 are our decision variable. And suppose the company has X1 units product 1 manufactured per week and X2 units of product 2 manufactured per week. And step 2, identify the operating function. And the profit per unit of production 1 is $56 and production 2 is $46. So the total profits of consuming X1 product 1 and X2 product 2 is max C equal 56X1 plus 40X2, which is the operative function. And step 3, identify and express mathematically all of the relevant constraints. Here we have 7 constraints. In our example, the constraints are the maximum raw material spare parts here. It relates to the spare parts and chair legs. These numbers come from this table. The maximum spare part G2, G1 is 1,280, and the requirements of spare parts, product 1 is 8 and product 2 is 4. So we have X1, 8X1 plus 4X2 is equal or smaller than 1,280. And similarity, the maximum spare part G2 is 4X1 plus 12X2 is equal or smaller than 1,600. And here's. So we have these numbers. And the next constraint is about the policy constraints. The policy constraint is about the number of units to be produced in weeks. And here we have X1 plus X2 is equal or greater than 100. And here we have non-negative constraints. The non-negative constraint, this is type of constraints, and it states that all decision variables must take on values equal or greater than 0. They include because X1 and X2 are the number of units produced, and you cannot produce a negative number of items, right? So we have these numbers. And so therefore the mathematical formulation of linear programming problem is, yes, include operative function, constraints. So now we move to the graphical method. Graphical method to solve a linear programming problem. And this method can be used when there are only 2 decision variables, and if there are 3 or more variables, so this method is not suitable. And in that case, we will use the more complex method, in which we will discuss separately in the next part. And here are steps for this method. Step 1 is formulate the linear programming problems and develop operative function along with all the constraints function. As we did this. And step 2, graph the feasible region and find the corner point. Feasible region is the common region determined by all the constraints and non-negative limitation of a linear programming problem. Is it an area of that satisfy all the constraints, And the corner points are in the feasible region that is intersection of two boundary lines. And the coordinates of corner points can be obtained by either inspection or by solving the two equations of lines intersection at that point. And step 3, make a table listing the value of objective function at each corner point. And step 4 is determine the optimal solution from a table in step 3. And if the problem of maximization types, so the solution corresponds to largest value of objective function is the optimal solution of linear programming problems. So if the problems is the minimization type, so the solution corresponding to the smallest value of the objective function is the optimal solution of the linear programming problem. So come back our example. So here's a graphical method to solve our example. So to find the optimal solution, firstly we draw the formulation of linear programming problem, and we have these lines. And then to find the optimal solution, so we identify the region of feasible solution and then the corner point of the feasible solution. And here's have a table. The corner point, as I said, is the intersection of two boundary lines. So the corner point is this point, this point, this point, this point, this point, this point, this point. So testing this corner point on the objective function, as we objective function here, 56x1 plus 40x2. So we have profit here. So you can see that the point 130 and 60 produce the highest profits. So we conclude that producing 130 units of product 1 and 60 units of product 2 will yield maximum profits.
Sorry for interruption. What is the orange area here?
The feasible region here is the green area. No, it's orange areas here.
Yes.
And so the another point, like another limitation of graphical methods is that an incorrect or inconsistent graph will produce an inaccurate answer. So one needs to be very carefully while while drawing and plotting the graph. So that's my part. So the next part will present by Thủy.
Good morning, everyone. My name is Thủy, and Jane has shown you the graphical method to solve the problem. And now I want to introduce another method, which is easier and faster, is using the solver tool in Excel. We have three steps that firstly write it out on paper, the model, then present it into Excel spreadsheets, and finally using the solver tool to solve it. And there is one advantage is that when the model is incorrectly formulated, the solver usually give an error when executing, so that we can correct the model errors. The solver tool in Excel is in Data tab. Here, if your Excel doesn't have solver, you can go to File, then Options, Add in, and click Go and then you just take the solver, add in. After that, it will your Excel will have the solver. Now we move back to our example problem 4. Chang has built for us the model already, so now I will present it into Excel. We will present the decisive variable. Decisive variable is the quantity of product 1 and product 2. We doesn't know it yet, so we just put a random value to show it. I will put 1 and 2. Then the objective is to optimize the profit. So profit of product 1 is 56 and product 2 is 40. And then the objective function. Objective function is equal to 56 x1 plus 40 x2, and it means that the sum of the profit of each product. So the objective function is the sum. I will introduce an Excel functions for faster is sum product, which means that you took the value in from this array to multiply with value in the other arrays respectively, then sum the total of it. It will easier and faster for you when using. Still have the same. And now step 3, the constraint. It have the same formula with the objective function, so we still use the sum product. This is a variable, fix them for later use. Then you just put it down. And then put the conditions smaller and equal. This file constraint had the same condition. We just put out, and then the total sheet. Is a larger or equal to 100. Now we will use the solver tool to solve it, because I have already done it before, so the solver remember my settings, so I will reset it all to show you. Firstly, set an objective is the objective functions. Okay. Remember that set objective need to be formulated to max, mean, or the value of a specific number. By changing variable cell is that our decisive variable. Then the subject to the constraint, we just add. We can add one by one or add group of them if it had the same conditions. In this case, it has the same conditions. Smaller or equals, you can choose the condition here. Int is an integrate, okay, and the constant, group them respectively, then add. For continue adding another constant, is total sheet not large, cannot smaller than 100. And one more decision, one more constant is that x1 and x2 large is not negative. X1, x2 negative. Okay. The select a solving method. There is a description about the method here, but this is a linear problem, so you can use any method because the result mostly the same. The option, you just leave it at default is okay. Then you press show. If you give the solver solution, this means that you all of the input decisive variable, our variable objective function will change. Any function related to variable will change too. And also the report is to for more information. Then okay. Oh, something wrong. Here. No, negative.
Sorry, you need to do a separate cell with you got the arrow, the array, so you can check on the array and you will put condition for on array. Okay, you don't need to check the cell, every cell in the variable for equal or greater 0. You check on the array of decisive variable, and you with the condition the greater or equal to 0. It's okay when you list every cell, but with the condition, with the constraint that you can put on the array, one condition is similar.
Sorry?
You understand what I mean?
I can hear you clearly. There is some miswork.
Okay. You can put the decisive variable. You want the decisive variable non-negative.
Non-negative.
Yes.
This one? Okay.
I mean, when you add the constraint.
Yes.
When you add the constraint, if you have the array of the constraint, you can check on the array with the one condition. You don't need to separate You don't have to separate every constraint.
Yes.
Yes. Okay, you just click OK.
There is something different here. Okay.
So you can check the formula of the
Yes.
adjunctive function and
I know. Yeah. Okay. Function here. So right. To max. So it might be something.
so you reopen the solver,
Yes.
and check it carefully. Yes. By changing variable cell. Okay. And the constraint. This first one. Okay. The third one, the third constraint.
A. Constraint smaller and equal to. Okay. Is smaller or equal to. Okay, maybe so.
This is not definitely our solution.
Yes, it's not correct. I try to do it again. Right. Some reduct. Function.
Thủy, can you open the solver?
Yes.
The last constraint you set lower and equal. They are greater and equal, not lower. Right?
Yeah.
Oh,
It's
yes.
a greater and equal 100 products.
My fault. I'm
per
sorry.
week.
Okay, thank you. Thank you, Như. So the answer report is correct now or not? Okay. That is.
Yes, it's correct.
Okay. So I will continue. For the answer report, we will have more information about there is the stated binding, which means it meets the limit. Indicated it reached the limit, the conditions. You can see the slack is the leftover inventory. Okay, here, leftover inventory. And the binding stated to show that we give us of information that the more binding stated we have is represent the model the better because we meet the conditions. meet the conditions. So this is the solutions for practice 4 on the LMS. After this example, we can note a few things that you should separate the input in Excel for better use in solvers, and also highlighted the decisive variable and the objective functions for easier use and also easier to notice when you see the model. I also like to highlight the left-hand side of the constraint for easier when entering into the solver. And now we move to another problem is optimize when capital budgets is limited. The information here is that we have 4 projects, and the table shows the cash flow of each project 2 to 3 years in futures, and the NPV of it. This NPV we can sometimes is provided, sometimes we have to calculate it. So in Excel, we have a function to calculate the NPV with the rate and the cash flow of the future cash flow, then plus with the initial investment. And our limited here is, our limitation is the investment capital in year 0s and year 1s do not exceed 100 billion, which means that the total investment in each year is smaller or equal to 100. And as you can see that in year 0s, the total investment capital needed is over 100, which means that we cannot invest fully in each project, but a part of it. So the question now is how to invest in each project, or what is the investment rate we should invest in each project so that we can achieve the most optimal profit. So we determine the decisive variable is that the investment rate, and let W, X, Y, Z be the investment rate in each project respectively. And our objective is to optimize the profit, which is the NPV, to have the maximum total NPV. The total NPV is the total NPV of each project, but we invest a part of it, a part of the project. So then we receive a part of the NPV, and then I have functions. The total NPV is equal to 6.48 W plus 5.33X plus 1.22Y plus 1.88Z, and the objective is to maximize it, and the constraint is the total investment capital in each year smaller or equal to 100. And one more condition is that our decisive variable is a percentage, so it's a rate, so it will be non-negative and smaller than 1. Now we will.
Hold a second. Can you clarify the investment rate in this situation? Because I think everyone in class maybe misunderstand the investment rate here.
Investment rate here is that we have a pie, we have a cake. So if we invest fully, then we buy the total a whole cake. But if we invest a part of it with a rate just a part, so we just buy a piece of a cake. So that piece over the case is the investment, is the same as investment rate.
So you need to show the very important assumption here. The assumption that the project, every project can be split into the smaller project. This assumption means you can divide the project into smaller parts and you just complete the smaller parts and you get the NPV for the smaller part of the project. So 100% proportion of the project, you get the 100% NPV of the project, but you don't need to cover the whole project. You don't need to do 100% of the project. You just do 20 or 30% of the project, and you get the corresponding NPV with that proportion. So the WXYZ here is the proportion of the project you want to do, because the project can be split into the smaller projects. So
yes. So I will continue.
And we're going to find the proportion of every project that we need to do, which maximize our NPV. So our NPV, you distribute the proportion of every project to the NPV of corresponding project. So you got the total NPV of the 4 projects. And we need to find out which proportion we have to invest. We have to put our money into the project to maximize the total NPV. So you got the objective function here. The NPV equals 6.48 W plus 5.33X plus 1.22Y plus 1.88Z. That's our objective function. Okay. And one noticeable things here you need to be aware is that the machine, the Excel, doesn't know our cash flow. So the cash flow is a negative and maybe a positive. Negative is we spend our money on the project, and then the positive is that we collect the money from our project. So the constraint, you focus on the constraint and you see we don't put the minus, the negative number here. We just put the positive number because the Excel doesn't know about it. And you change a little bit the formula a little bit from the negative number to the positive number. We have the total spending, the total funding for the year 0 is 100, the negative 100 million, 150 million, but we don't write down the negative number. We just put the positive number is a 70W plus the 80Y is the equal or less 100. So remember, you have to change the equation a little bit to make sure the Excel know the information. Okay, continue.
Yes, we will format it as percentage and also give a random number to present the variable. The objective function. The objective functions are the maximum total NPVs, maximum total NPV maybe is equal to the functions. Here's and it has the same format with the sum product, so we can use the sum product like it. And then general highlight it and the constraint total budget. Is as our teacher has said that because this table only represent this table represent the cash outflow and the inflow. It's not the Excel doesn't know it, so we have to put it into the value of it, but the Excel we just put the minus before it for easier. But this is not correct. Do you know why? Because we only invest a proportions of the project, so we cannot calculate the sum of it. But we have to take each of the budgets to multiply with the proportion. Okay, so and because as we can use the sum products again. Is okay, generated with the forms and put the constraint value. It must be smaller or equal to 100. The same in every second, and also the WXYZ is non-negative and larger than can be and smaller or equal 1. Then we use the solver. So reset all. Set objectives is the objective function to the max by changing variable cell variable subject to the constant. We have the same condition, so we can put here, right? And then the variables smaller or equal 1 or and non-negative. Then we solve it. So with this proportion, we can have the maximum total profit of 11.9. This is the solutions on the practice files on LMS. So this is the end of my presentation for.
Wait a second.
Yes.
Can you show me the sensitivity report and the limited report for this case? Yes. And you explain everything in the sensitivity and limit report here.
Okay.
So the first one is the sensitivity report.
Yes,
what does it mean? Yes, you can explain. Sensitivity report.
I'm sorry, I don't know these columns.
Okay, you don't know the sensitivity report,
Yeah.
and you don't know about the reduced regression and Lagrange multiplier.
Yes.
I can tell you in our class that the sensitivity report is very useful when you want to find out the variable chain leading to our objective cell, our objective function chain. So you can see here in the sensitivity report, we have two tables, the variable cells and the constraints. So when you look at the variable cells, we realize that the column that's reducing gradient. So the reduced gradient show us when the variable change one unit and the objective function change the number of radial gradient units. For example, when w, x, y, z here, when w variable change one unit and the total MPV, the objective function change 3.71 unit. So it's a show us the sensitivity analysis between the decisive variable and the objective function. So you can say when every decisive variable change, you got the how much the objective function change. And the constraint, the table constraint show chain of sensitive chain of the constraint, the right hand side leading to the chain of the objective function. So you can see the Lagrange multiplier have a similar process of the reduced gradient here. And when we increase or decrease the right hand side of the constraint, and the objective function will increase or decrease the Lagrange multiplier. So the sensitivity, you understand the name, the sensitivity, which give us how much the objective function change when change the variable or the constraint, the right hand side of the constraint. Okay, but in the linear programming, in the linear optimization, we have a little bit different compared with the non-linear optimization. But you see, the sensitivity have the same goal, the same purpose, that we can know how much the objective function change when the variable or constraint the right hand side, the right hand side of the constraint change one unit. Okay. How about the limit report? You know the limit report?
No, I only know the answer report.
Yeah, the limit report give us the lower and the upper limit of our objective function. So you can change the variable, you can change the decisive variable, and the lowest limit and the upper limit of the reserve you can see here is with responding WXYZ variable is 542 or 694. This is the objective function when we get the lower limit or the upper limit of our variable, our decisive variable. So in the linear optimization, focus on the answer report and sensitivity report, because two kind of reports is very important and very useful to analyze all the result of our optimization model. Okay. Yes, keep on.
Yes. This is the end of the linear optimizations. So now we will move to the non-linear optimizations, which is part of Nhi and Như.
Oh, sorry, I want to ask you one more question. And you can see, can you turn back again your practice? You can just share your screen again. Yes. So in this case, in this situation, we have a very important assumption that every project WX, YZ can be split, can be divided into smaller project, smaller parts. So we can do a percentage, a proportion of the project. We don't need to do all the project. But if I change the assumption, if I change this assumption, I don't want the project here can be split. So if the assumption that the project cannot be split, cannot be divided, so how you can handle this assumption in this case, in this situation? So the proportion cannot be between 0 and 1. Is a 25% or 27 or 75%. Is it cannot be that number. The proportion must be 0 or 1, because we cannot split the project. We cannot divide the project into smaller parts. So show me how you can handle this assumption. So the decisive variable here, WX, YZ, just can be 0 or can be 1, just two values. Can you open your mic? Your mic.
I'm sorry. I'm sorry. So I will change the constraint to binary so that it can only receive two values, that is 0 or 1, which means yes or no. Yes.
Okay. So you change the constraint, and you can show it again for our class. Yes.
Yeah. So I will change the constraint that the variable now will only receive two values, that is 0 or 1, which represent for yes or no. That is bin.
Is the bin represent the binary? Yeah, binary. That means you just got the two values, 0 and 1. Okay.
Yeah. Then solve it. Okay. So now it's show us the solution 0 and 1 only. That means that we should to have the maximum total NPV, we should only invest in a project W and Z,
Yes.
and we don't invest in project X and Y.
Okay, thank you.
Continued part is a nonlinear optimization, which will present by Như and Nhi.
I will continue our group presentation with part 2, nonlinear optimization. So what is a nonlinear model? A nonlinear model attempts to relate the value of dependent variables to independent variables using an equation. A nonlinear model describes nonlinear relationships. That means a change in one variable does not correspond with a constant change in other variables. For example, the existence of non-proportional relationship, we have the formula below. Revenue equals quantity multiplied by price. Different prices can change the amount of products. However, sometimes price and quantity do not move in the same direction. For example, when the price increases to a specific point, the quantity may decrease because the demand of buyer decreases. Another example is about economies and diseconomy of scale. This economy of scale are when the output increases. For example, in the picture is from Q1 to Q2. Then average cost will increase from C1 to C2. Conversely, economies of scale are when the output decreases and the cost per unit of production decreases too. Next, we will see how a nonlinear optimization presented over graph. In nonlinear programming, solver uses the hill climbing method. The hill climbing method starts with the first point, which has been selected before. Then it moves in the direction of increasing value to find the maximum value of the problem. This is local maximum and global maximum. Local maximum is a state which is better than its neighbor state, but there is also another state higher than it. However, global maximum is the best possible state. It has the highest value of objective function, and it is the point which the method attempts to find. We have another example of a nonlinear optimization problem shown in a graph. The objective functions is x1 minus x2 move to maximum, and there are 4 constraints. And among these constraints, the first constraint, that is minus x1 squared plus x2 is more than or equal 1, is nonlinear, and the others are linear. You can see that the feasible region is the green area. It is limited by the curve, that is the nonlinear line, and 3 straight lines, that is constraint line. The point in which objective function and nonlinear line intersect is optimal value. We will make a comparison between linear programming and nonlinear programming. There are 3 similarities. An increase or decrease in the right-hand side of the inequality will loosen the constraint and expand the feasible region. The second one is that loosening the constraint increases the optimal value. And the last one is tightening the constraint can damage the optimal value. About differences in a linear model, a local maximum is also a global maximum. But on the other hand, a nonlinear model has both a local maximum and a global maximum. The second difference is a linear model helps to find a solution to the problem using constraints that are all linear. However, some constraints in a nonlinear programming may be nonlinear. In a nonlinear model, not any local maximum is also a global maximum. You can see in the picture I have shown in the slide. The global maximum is the maximum value based on global constraint because the value of objective function at this point is the largest of all possible points. In a linear model, to find global maximum from local maximum, convex and concave conditions need to be added. These conditions must be satisfied to ensure that the local optimal value will also be the global optimal value. So how to use solver for nonlinear model? While in linear model, solver uses the method that moves from corner to corner in feasible region. In nonlinear model, solver use the hill climbing method. The steps of this process are as follows. The initial values of the variable are used to decide a possible direction to quickly improve the value of objective function. Then solver tries a new direction from a new starting point. The above process is repeated until the optimal value no longer improve in any new directions. And to see how solver apply to solving nonlinear problems will be presented in the next 3 parts by UEH. And that is the end of my part. Thank you for your listening.
So I will continue with the next part. Like Nhi said before that not all the relationship between the economic variables is linear. There are some cases that that relationship are non-linear. So we have to use different methods to do the optimization model. And so then in this part, I will show you some way that investor use the non-linear optimization model and apply to the real situation in our real life. So first, the investor often use this kind of model, to manage the portfolio. So what is the portfolio management? According to the definition of one popular economic website, that Investopedia, it is say that portfolio management is the act that you have to select and pick some potential asset in for you to invest that meet the long-term financial objective and with some condition for the risk tolerance of the client, of the company, or in situation. So when one investor do the portfolio, they often consider some constraint here. The first is the total weight or the total percentage of the asset you invest that must be summed up to one, or like the teacher said before, this total weight maybe less than one. It depends on the demand of the investor. The second constraint that the diversifiable portfolio, which means that you have to invest in many assets, like greater than one asset. If your portfolio have two assets, at least you can call it that diversifiable. And the third constraint is related to no short selling. So you can, to all the knowledge, you already know that short selling is that you buy the stock from someone who is broker and you sell it for another, you receive money, and you expect that the price of that stock in the future will decrease, and then you buy back again and you pay that stock for the broker that you borrowed before. So that counts short selling. So in the meaning of this constraint in the portfolio management, that during this portfolio you cannot just sell the asset you invested before. The next constraint that I say that the total investment capitals that maybe less than the 100% of money you have. You can just like invest about 80% of money you have for that portfolio. And the last constraint that very kind of important, that when you invest something, you always want to the rate of risk that less than the threshold, and a rate of return must be greater than a threshold, and it's also depend on your demand, investor demand. And that's for some definition in knowledge about portfolio management. And now we go to the detail of we construct the optimization model for the portfolio of two stock, that the stock 1 and stock 2. I just don't mention the specific number. I just like I will show you the economic variable description that we often use to construct this model. So here are some of the variables we will use to construct the model. The first is XI. It represents for the percentage you use your money to invest for one asset in the portfolio. The second is the standard deviation to the power of 2, which is also the variance of that stock. The third is the RI. RI here is represent for the expected return that one asset can give you. The next is covariance between the rate of return of these two stocks. B is the least requirement for the whole portfolio return. And the last one is SI. SI here is the maximum money or maximum percentage of money you should invest it for one asset. And you have also determined the decisive variables, which here is the portfolio weight of asset, that S1 and S2. So next, after we find some constraint and object and the changing variable, we need to set the objective. So when we invest something, that we also want to look for the the minimum risk or cost and the maximum value of revenue or profit. So normally, when we consider the risk of one portfolio, we often consider the variance of that portfolio, because you know that in the subject statistic that we studied before, that when the value, the ideal value of that portfolio return will be right here, the middle line. But in real situation, there are some risk that make the value of that expected value fluctuate between around this area, depend on the strength of that risk. So so we have the objective function here with each the portfolio variance that we set to minimum. I will explain you why we have this function later than the Excel practice. It relates to kind of like the matrix of variance between the asset in the portfolio. So here is the specific constraint which is used the decisive variable to set up. You can see here the capital is fully invested, that the on the way sum up to 100%. And here is the least requirement portfolio rate of return. This is the rate of return 1 and 2 multiplied with the I can say that the probability for that return. So this is the requirement. And here is the threshold for each asset that we should invest in. Now for the asset 1, asset 2, and we also consider the constraint that no short selling. That means that during the period of portfolio, we shouldn't sell any asset for another one. So, and I will show you some calculation in Excel file later. The next case that the investor often use the nonlinear optimization model to be applied, that the economic order quantity, or we often call it EOQ in the corporate finance that we studied before. So what is EOQ? EOQ here is the ideal quantity that one company should order from the supplier to minimize their costs. There are some relevant costs like the holding cost, the structured cost, and the other costs. So the relevant costs, like I say that we have the other costs that include the cost of delivery, the cost of trading with the supplier. The second is the holding cost, that include all the costs that we store our goods in the warehouse, and it's often calculated based on the input price that we pay for the supplier. And the last relevant cost in this model is the stock out or the stock shortage cost. This cost occurs when the demand of the customer is greater than our supply. So that's it. So how we find the ideal quantity? We must look for the equation that we set up follow here. That we consider the goods we order from the supplier. We often count the average of goods here during one period. One period here can be the 1 year, 1 month, 1 quarter, everything that you want, but I just count it one period. So at the first period, we order the Q, and at the end, when on the goods are sold for the customer. We have 0 goods on our warehouse. So and identify at the end that we have the average of good equal to Q divided by 2. We can see is the holding cost per unit of good. So the total holding cost equal to the average of good multiplied with this C, and we call it is the total holding cost. Next, we need to consider the other cost. Before that, identify the other cost, we need to identify the numbers of purchase order that we make to the supplier. The numbers of purchase order is calculated by take the S divided by Q. S here is the total demanding numbers of goods from the customer, and Q here is the numbers of ideal good that we say before. So we call the O here is the order cost for one purchase order. So the total order cost we have the follow here, and so we have the total cost, and we consider the holding cost and the other cost that equals to this equation. And we need to, because we often looking for minimize the cost, so we need to set up this total cost into minimum value. And the constraint for this model is kind of easy, that we just set the Q or the ideal quantity greater or equal than 1. So for you to clearly imagine or relate, this is the graph illustration. You can see here, by this quantity of good, you can minimize the total cost, the holding cost, and the other costs. So now I will illustrate some example in the Excel practice. Can you still hear me?
Yes. Yes. Yes.
Okay. So I will delete the quantity. And this one too. This one. So this is the given information. The given information that the holding cost we can see equal to the 24% of the input price. So we will calculate it. It is the input price for 1 unit of good. So the holding cost for 1 unit of good equal to this amount multiplied with this amount. And equal to $1.92 for 1 unit of good if we store that good in the warehouse. So we need to calculate some the total of the other costs, the total of holding costs, and the total money that to have paid for the supplier when we get that goods. So this is calculated by the S divided by Q equal to O. S here equal to 60,000 unit of good. And O here equal to $25 for 1 purchase order. So we make the calculation that equal to S divided by Q. We put the number here, and we will use the solver to solve them later, but we need to put the specific number here first. So I put 1 here equal to X divided by Q multiplied with O. For the holding cost, that equal to the half of quantity multiplied with C. We have Q here divided by 2 multiplied with C for 1 unit of good here. And total money you have to pay for the supplier equal to S multiplied with input price. So the total cost equal to sum of this cost. We use the solver here to find out the ideal quantity here. So I said before that we set the objective, that total cost, to minimum value, and the changing variable is Q, and the constraint is just Q greater or equal than 1. So we press the so button. And now, so here we get the solution, that the ideal quantity that we should order from the supplier equal to 1,350 unit of goods. And this is an example for the EOQ model, which is applied nonlinear optimization modeling.
Sorry, how to make sure your number Q will be the integer?
Sorry, what will be what?
How to make sure your number Q will be an integer? Maybe it's the decimal number.
I think that we set the constraint in solver. I just didn't consider this situation.
Because the Excel doesn't know the number of Q will be an integer.
Yes.
Number of the product, number of the inventory. So you set the constraint to make sure your decisive variable will be the integer. Yes.
Yes, here equal integer.
No. You put the int. Yes, the integer. Okay. So it's always be an integer, not a decimal number.
Yes.
Okay.
Thank you. So I will now move on the next example that related to the portfolio management for the 2 assets. Because it's I calculated before, so I will delete it. So here is on the given information that we get to we use some methods to find out the solution that make this portfolio variant to be in the minimum value with some certain weight here, weight or xi here, or changing variables. And so before that, we need to calculate some related numbers, like the average expected return of each asset that can give you. So I use the average function here to calculate average expected return of AT&T stock. And So we have the expected return for each stock here. Now we because this is the changing variables, so we will put on the initial value like 1% or 2%, and we will let the solver calculator then. So I will put the 1% here. So this is the requirement for the total percentage for each asset that is lower or equal than 75% for on the 3 assets here. So the expected rate of return for the whole portfolio will be calculated by using the sum. You can use the sum product. Which is equal to this in this rate. And here is the total weight that must be summed up to 100%, which means we fully fund for the portfolio. I will so there is one thing important left here, that we didn't fill the matrix of variance here. I will explain you some mechanism related to this matrix. That in the first row, we have the name of 3 stocks, AT&T, and I write that AT for short, GM, and the USS. And in the first column, we also have the same order of that name of those stocks, AT, GM, and US, that we need to fill the variance of these stock or the asset. The first, we can see here, because AT&T is the same asset that equal to the standard deviation multiplied with the standard deviation of itself, or we have the standard deviation to the power of 2, which is the variance also. Because each of standard have the weight I say before, that we need to mention when we fill in this matrix. This is the fundamental form. But when we fill in this form, we need to consider the weight here, because we use 2 times of standard deviation, which means that we have to power to the 2 of this way, and so we use the function that's variance of this variance P of this asset multiplied with itself, the weight of itself, and to the power of 2. You can see here the diagonal here is the variance of that asset itself. So we repeat the step with the corresponding weight. So with the GM asset, we also use the VAR P to calculate the variance of the asset, and multiply it with the weight itself to the power of 2, and the same step with the asset, the last asset, the USS. Okay. This way to the power of 2. So we finish the diagonal line here. How about the other blank, the other blank that have not filled yet. So here you can see, because this is the variance between different two assets, so we need to use the other technical term that covariance between these. So because the covariance, we can use the function 2 because it's from the different two assets. So which means that we use the probability of each standard. We don't use the we don't use the to the power, but we multiply the weight of asset together. Like here, AT&T with the asset GM, I will use the covariance P of the two assets, that A and G, multiplied with the weight of A multiplied with the weight of G, so it's equal here. And this is, so the next is covariance between AT&T with the USS. So we use the covariance. We repeat the step with the information of AT and USS, multiplied with the weight of AT&T and the weight of USS here.
Sorry, guy.
Yes.
You don't need to multiply to the weight here, because in the covariance, you find the relationship between AT&T and GM, or AT&T and USS, and the proportion, the weight of every stock doesn't include in the covariance.
Yes, but because if I do not fill the weight here, I have to another way to show that, use some kind of function multi related to the product between the matrix. So I think it's kind of complicated. So
okay, keep on. I will fix you after you finish this.
Yes. So because it's the same, so it's equal to this amount and equal to this, and this is equal to this. So we already filled on the blank here, so we next will use the solver to find out the...
Sorry, just hold a second. We check your covariance matrix, and the one way to check the covariance matrix.
Sorry, I can hear you clearly.
Can you hear me?
Yes.
Okay. We need to check the covariance matrix here. One way to check your result is using the data analysis. You can
yes.
use the data analysis.
Okay, I will use this.
Okay, and you select the covariance, and you input on the table of the
So we can use another way to find out the covariance, the asset.
So we can see it's the difference between your way and this way.
Because it's related to the weight here, but the weight here is not calculated yet, so this may not equal to this. But when I will solve, I will get the same result.
Okay. Keep on.
Yes. And so we have we fill already the matrix here. So we just sum up on of the information in this matrix that equal to the portfolio variance. We don't need to multiply with the weight again. Just sum up all of this into one here. So I use the solver and I explain the constraint and objective. We need to set this variance into the minimum value, and the changing variable cell here is equal to this. For the constraint that this array, for each element of this array must be lower than the maximum percentage for each asset here is equal to 75%. So I set here. And next is the I'm sorry, wait a minute. C19 here to the next constraint, that which means that we do not conduct any short cell which the each way greater than 0. The next is the total sum of the weight of asset must be summed up to 100%. And the last constraint related to the requirement return for the portfolio, which is greater than 15% here. So I press the solve here to get the value. So we will get the variance, the portfolio equal to this amount with these changing variable cell. You can see here, and you can see that it's in my covariance matrix. Yes and no.
So is
yes.
the same with your result, or is it different, the covariance matrix?
I don't know, but why it's different, because I did calculate it last night. It's equal, but yeah.
Did you forget any constraint?
I will check it again. Solver.
So I'm so curious that you allocate the changing variable, allocate the weight into the covariance matrix like you did.
Yes.
Because it's I think it's not we separated the covariance matrix and the variable, the changing variable matrix to set up our objective function.
Yeah, we can. I think that there are many ways to get the solution. So if you want me to do it in that way you mentioned, I will recalculate it.
Yes,
but
because one of the formula we need to learn here is the portfolio variance, the formula for portfolio variance between we use the two matrix multiply
yes,
with the proportion matrix and the variance, the stop variance, the stop covariance.
But can you tell me that is it the correct number?
I think it's the correct. Yes.
Yes. So I will recalculate in different ways. So we repeat the calculation at average. Oh, no. Trời. Sao lại kéo cái này? We delete the number here. So we use the data analysis to fill this matrix. Covariance tools. You click OK, and you put the input range here, and you export it into another area. Okay. So here is the covariance matrix. Covariance matrix for the portfolio, for each asset of portfolio. We copy the data here to this. But why you can see here that we still have the blank here. But you can see that this is the covariance between GM and AT, and it equal to covariance between GM and AT too. So this equal to this, and this equal to this amount, and this equal to this amount. So we have to put the initial amount of the weight, like 10, just randomly fill in, and the expected rate of return for the whole portfolio equal to the sum product of the average rate of return of each asset with each weight, corresponding weight. So we don't use the method that sum on the information here, but we use another way that we use the function that multi. We write here multi here, which means that we do the product between the matrix, like two or three matrix. And wait a minute.
M moon here is the brief for the multiplier. The multiplier you want to multiply between the two matrices. You use this function M moon.
Yes, and we use this function. That you should open the Excel file and follow with me to catch up with. So we moved of this matrix, this big matrix, with the matrix of weight, the array here. No. you have to input 2 times of month. The big matrix and the second matrix of weight here. Also, and you need to input the demand of transpose of this weight of this weight. So, but we don't press the enter button. We have to press the 3 button at the same time. That Control, Shift, and Enter. Oh, why don't we get the result here?
You need to put the weight matrix first, because you know, the vector is
You
when
mean
you
in here?
when you study the matrix. Yes, the weight matrix. Yes, the row first, and then the covariance matrix.
Okay.
Transpose is a wrong function. You transpose with S. Transpose.
Yes.
Transpose.
Transpose. So we okay, and we now set the constraint and the objective for the solver to get the solution. Right, we will open. Oh, trời, sao nó... So the objective that this portfolio variance to be minimum value, and the changing variable cell here is the weight of each asset. So the constraint is that each weight of asset must be lower than the 75%. So I have the constraint here. The next constraint that that the total sum of this weight equal to 100%, which means we fully invested for the portfolio from the money we have. And the last is the constraint for the expected rate of return of the portfolio, which is greater than 15%. And now we press the solve here. Why is that? Okay. It's kind of different from the first answer. I don't know why, but
it's a wrong answer, not
yes.
the optimal solution.
Yes.
So you can check the solver again. How about non-negative for the changing variable?
Non-negative of weight.
And
what else? I think it's enough. I will solve later again. Oh, still get the same result.
how about the verifiable constraint?
Sorry,
on the changing variable, less than 70%. You got that constraint?
Yeah, if I say that I do that, it's already add before here, right? I delete it and add again.
Yes.
And here, one. I don't know if the comma on the point. Okay.
The point.
The point.
Yeah.
Here. Also. Oh. You can help me to check the function here again.
Không biết có phải là do cái ô mà chị em nhân với USS nó phải là phần trăm không? Mình phải đổi nó ra số thập phân không?
Okay.
Matrix. You can show me the formula. Just multiply. It's multiply. Okay, transport.
Mà sao cái ô đó nó không bằng với cái ô USS nhân với chị em vậy?
Okay, I get the this equal to this.
Yes, you asymmetrical in the covariance matrix, and you push the wrong number here. Yes. Okay.
Sorry, I'm sorry.
So
we saw
you
again.
see in the correlation matrix and the covariance matrix, we get the asymmetrical between the diagonal. You remember when we have the same number, the same value in the diagonal.
Okay, we get the right value here. And that's on about the example that I calculated for you to clearly get how we apply the nonlinear optimization model into the real economic situation.
In fact, in this situation, we have the easier way to calculate the portfolio variance.
Yes, I will show you another way that we use the portfolio.
When you have the return of the stock in every period, and you can calculate the return of the portfolio in every period, in every year, and use the VAR function, to get the variance from portfolio. Is very easy. Then you use the covariance matrix to calculate the portfolio variance. So you can see, just use some product between two areas, the weight, the return of every stock in every area. As you just get every portfolio return.
Yes.
So you can calculate the portfolio return and portfolio risk, portfolio variance, very easy.
So this is the same with this amount. We can get this amount. We can set this amount to our objective, and we use the same constraint with this matrix. Do we need to calculate with this?
Yeah, no, not necessary. Not necessary.
Yes. Okay.
I just want you to know that the variance we calculate this way is a very exactly value of the variance we calculate from the covariance matrix.
Yes. So this is on about our presentation today. So if you have any question, just open the mic and ask us. We're ready to share with our answer for you.
Okay, thank you. Thank you all of you, group 3. Yes, your presentation is a very interesting and very accurate information for us. You provide the theory, the background from the linear optimization and non-linear optimization. And so you give us some example, very typical example for us to apply how to solve, how to calculate, how to optimize the problem in reality. And I want to recap a little bit about our content today. As you know, we have the two kinds of optimization model. The one is the linear optimization model, and other is the nonlinear optimization model. So the first question I want you to answer: what the basic difference between the linear model and the nonlinear model? And when you determine what is the linear model and what is the nonlinear model, so you can use the relevant error range, to each models, and it's give us the best solution, the optimal solution. So when you decide what is the linear model and what is a nonlinear model, just very simple question.
I would like to answer that first the linear model, that which means that the relationship between the independent variables x with the dependable is between that is the to the power of 1. And for the nonlinear, we have the rest of relationship like to the power of 2 or 3 or log neighbor or something that different from the power of 1 in the linear model.
Yes, I know what you mean. That is the relationship, the difference between the relationship linear and nonlinear. But I want to know how we use linear optimization and how we use the nonlinear optimization. Which case we use the linear optimization?
I think that when we set the objective or the constraint for the model, if there are just one function related to the nonlinear function, that we have to use this model in the nonlinear optimization.
Oh yes, that is correct answer.
Yes.
So notice that when you encounter any relationship, any nonlinear relationship in the objective function or in the constraint function, that's you have to use the nonlinear optimization. Okay, and you can see our typical examples here is about the production planning and the capital budgeting in the limited capital situation. So it's a very typical and very simple case to apply solver to apply what we know about the linear optimization into the reality. And about the non-linear optimization, we use the portfolio models to represent, to show us how to calculate the optimal solution for the portfolio models. So in the portfolio model, we have the term such as the portfolio allocation. What is the portfolio allocation? The first session I just told you about portfolio allocation. That is to distribute the proportion, the weight of every stock in the portfolio. So in this case, we want to optimize our portfolio variance, which means we want our portfolio variance have the minimum value. So, and it's the model give back to us the weight of every stock in the portfolio. So that is the portfolio allocation. And with many constraints, you can add more constraints to the portfolio models, to the portfolio optimization, to make sure that the constraints is very relevant to your model. Okay, and that's all. That's all about the optimization and the linear optimization and the non-linear optimization we have a study today. So a little bit evaluation about our group 3 for presentation. I think your information is very adequate, is very relevant for us in this chapter, and just a little bit lack of skill in the practice in the case study, but isn't not much. It's still okay. So I give you 9 marks for your presentation for all of you, 4 members of the group 3, because I think we have a limited time to prepare this content, this chapter, but you already did it very good, very well. Okay, so congratulations, group 3, with the 9 marks from me.
Thank you, teacher.
Yeah. About the practice, I encourage every member of our class just take a little bit of your time to redo every case study in this chapter, in this content. And if you have any question, if you have any obstacle or any hindrance in applying what we learned, what we studied today into solving those cases, just tell me and give me your question. I will answer. Okay. So we will stop this session here, and I hope the another groups in the class will prepare well for the next content we will discuss. Okay. And we remember, send me your presentation, your slides, maybe at least 1 or 2 days before we start the session. Okay. Thank you. Thank you for joining with me today. Thank you, group 3.
Goodbye, teacher.
Yes, goodbye, everyone.